In the last presentation, we saw how to design the synchronous counters, and we also took one example in which we designed the 2-bit synchronous up counter. In this presentation, I will follow the same steps, the 5 steps that I explained you, and we will design the 3-bit synchronous up counter. So the step number one is to determine the number of flip-flops to be used, and also we will decide the type of flip-flop. So what we will do, we will determine number of flip-flops, and we will decide type of flip-flop. So these two things we have to do in step number 1, and you already know the number of flip-flop is proportional to the bit of the counter, and here you can see we have to design 3-bit synchronous up counter. So the number of flip-flop is equal to 3, because this bit is nothing but the output of the flip-flop, and as we have 3 flip-flops, we have 3 outputs, and thus the 3-bit of the counter. And I want to implement this 3-bit synchronous up counter by using the T flip-flop. So we are done with this step number 1, and now we will move to the step number 2. And step number 2 says we have to make the excitation table for the decided flip-flop. And we have decided T flip-flop, so we have to make the excitation table for T flip-flop. So let's make it Qn, and Qn plus 1 are the 2 inputs, and the output is T. We have 2 variables, so 4 possible combinations: 0 0, 0 1, 1 0, and 1 1. Now we have to find out the value for T. When Qn is 0, Qn is my present state, and Qn plus 1 is my next state. When present state is 0 and also the next state is 0, it means the memory, the T is going to be 0. And when Qn is 0 and the next state is 1, it means we have toggling, and for toggling the value of T must be 1. And for the third case also we have toggling, and for the last case we have 0, because next state is same as the present state. So this is the excitation table for the T flip-flop, and step number 2 is now over, and now we will move to the step number 3. Step number 3 is, and in this step we have to do 2 things. The first thing is to find out the state diagram, and the second thing is to find out the circuit excitation table. So first we will find out the state diagram. 3-bit synchronous counter we have to design, and for 3-bit we know the number of state is 2 to the power 3, that is 8. So there are in total 8 states, and the maximum count is 8 minus 1, that is 7. So our count will start from 0 0 0 and it will end at 1 1 1. So let's make these 8 states first, then we will make the circuit excitation table. This is our first state, 0 0 0. This is our second state, 0 0 1. Then we have 0 1 0, then 0 1 1, 1 0 0, then we have 1 0 1, 1 1 0, and finally we have 1 1 1. This is our maximum count, and you can see we have to make the up counter. So the counting will start from 0, then we will have 0 0 1, 0 1 0, that is 2, then 3 4 5 6 7, and again we have 0. So this is the state diagram, and by using this state diagram we have to make the circuit excitation table. The first column of the circuit excitation table is the present state, and the present state is given by the 3 outputs, that is QC, QB, and QA. Then the next column will give us the next state, and S is the next state, and next state is QC plus, QB plus, QA plus, and then we have the flip-flop input, TC, TB, and TA. So these are the 3 columns in our circuit excitation table, and we will find out the value of the flip-flop input by using the state diagram, and then we can implement it by using the K-map. when we are having the output as 0 0 0, you can see we are going to the next state, that is 0 0 1. So the next state is 0 0 1, and when we are on 0 0 1, the next state is 0 1 0. 0 1 0. It is very easy to find out the next state for the counter. If we are on 0 1 0, the next state is 0 1 1, and when the present state is 3, that is 0 1 1, the next state is 4 1 0 0. If the present state is 4, the next state is 5. If the present state is 5, the next state is 6. And if the present state is 6, the next state is 7, the maximum count. And if the present state is 7, the next state is 0. We are again back to 0. So this is what we have derived from this state diagram, and now we will find out the value for TC, TB and TA. First I will find out the value for TC, and it is nothing but the input to our T flip-flop, and for that we have to compare QC and QC plus, that we can do from this table that we derived earlier. This is the excitation table, this is the present state, this one is the next state, and by using it we can have the value for T. So let's do it. For the first case, QC is 0 and also QC plus. So present state and the next state are same, it means the memory, and in T flip-flop we have memory when the TC is equal to 0. Similarly, you can see for the second case again we have the same state, and for the third case again the same state. For the fourth case there is toggling, the present state is 0 but the next state is 1, and for toggling TC must be 1, and this case is having the present state 1 and next state as 1. So again we have the memory, and for this case also we have TC 0, and the second last case TC 0, and the last case we have toggling. In the same way I will complete TB 0 0, so 0 0 1 toggling, so TB is 1 1 1 same state, so TB is 0 1 0 toggling, so TB is 1 0 0 again same state, so TB is 0 0 1 toggling, TB 1 1 1 again same state, so 0 1 0 toggling. And for TA you can see we have always toggling 0 1 1 0 0 1 1 0 0 1 1 0 0 1 and 1 0. So I will write TA as 1 for all the 8 cases. Okay. Now we have TC, TB and TA. We can use a 8-cell K-map to find out the minimized value for the 3 inputs. So I will just paste a 8-cell K-map, and definitely we require 3 such maps. So I will paste 2 more, and the inputs are QC, QB, QA, 0 0 0 1 1 1 1 0 0 1, and this is for TC. TC is 0 0 0 1 for the first 4 cases, so 0 0 0 1, and for the last 4 cases it is 0 0 0 1 0 0 0 1. We have a pair of 1 here, and thus TC is equal to QB QA. Now we will solve for TB. The inputs are QC, QB, QA, 0 0 0 1 1 1 1 0 0 1. It is 0 1 0 1 initially, so 0 1 0 1. Then we have 0 1 0 1 again, so 0 1 0 1. We have group of 4 ones, thus TB is equal to, you can see QC is changing from 0 to 1 and QB is also changing from 0 to 1, only Q is not changing and it is 1. So I will write TB equal to QA, and now we will solve our last K-map, and this is for TA. The inputs are QC, QB, QA, 0 0 0 1 1 1 1 0 and 0 1. It is 1 for all the cases, so there is no problem. In this map we have the group of 8 ones and TA is equal to 1. Now we will implement it, and this is the last step. the implementation, we have 3 flip-flops, 3 T flip-flops. I will make these 3 T flip-flops. This is my first flip-flop, this one is second flip-flop, and this one is third flip-flop. Now we will implement the logic that we have evaluated from the K-map. This is the A flip-flop, this is B flip-flop, and this one is C flip-flop. TA is the input for the A flip-flop, QA is the output of the A flip-flop. Similarly, TB, QB, TC, QC. And as we are designing the synchronous counters, definitely the clock is simultaneous. So we have to give a common clock to all these 3 flip-flops, and this is the way to do it. This is clock, and now we have to implement the logic. First I will implement TA. TA is 1, so I will simply give the logic 1 to TA, and TB you can see is equal to QA. So I will make TB equal to QA, and I will simply join them, and TC is equal to QB QA, and we have to use an AND gate for this. So I will use an AND gate here, and the input to this AND gate is QB, and the second input is QA. So I will take QA from here and give it to this 2 input AND gate. The output of this AND gate is then given to TC, and you already know the output for the clock is QA, so we have to take QA, and QB is the second bit, this is LSB, and QC is our MSB. So QA, QB, QC output of the counter, and they will start from 0 0 0 and they will end at 1 1 1. In this way you have to design a 3-bit synchronous counter. I hope you got these things, and if you have any problem relating to this presentation, any doubt, you can ask in the comment section.